Hello, this is the Basketball Law with Lab Quiz of Physics 2212, and today we're going to be working with magnets. To start off, um, our goal today is to observe the effects of a magnetic dipole field, as well as the relationship between the distance and the field. And we're going to be doing this using the Biot-Savart law and several other fundamental physics principles. Now, brief peer review, we're going to find that our mu to be 0.1973 and our n is 0.0146, and that's negative. Okay, so some other fundamental principles we're working with today is the magnetic dipole model, the Biot-Savart law, as I mentioned before, and the distance dependence formula. Our system is the bar magnet and the magnometer, and the surroundings is everything else. Our initial conditions are shown on the screen. You see the phone is lying orthogonal to the Earth magnetic field because we need to minimize the effect that the Earth has on the magnetic field that we're finding. And we did this by rotating the magnometer until the x-component was very, very close to 0. Here we are finding the position of the magnometer by sliding the phone along the ruler to find where the magnetic field is the greatest. We mark that with a piece of tape. We then rotate the phone and repeat. This will give us a location of the magnometer in the phone. To perform the experiment, we find the on-axis distance from the bar magnet to the magnetometer for various magnetic field values. We then enter these values into a spreadsheet, take the average, and linearize the data by taking a natural log of both sides of the distance dependence formula. For the off-axis field, we do essentially the same procedures as in the first part, except we slide the magnetometer in a perpendicular direction, so we create a 45-degree angle with the horizontal. We observed that when the magnetometer was far away from the magnet, it measured a near-zero magnetic field, which can be due to the fact that the magnetic field was probably negligible at this distance. As the magnetometer moves closer to the magnet, the measured x-component of the magnetic field increases. Here we are doing some simple calculations using the linearized distance dependence equation. We know our slope of our graph is given as negative 0.0146, and we know our natural log of k is negative 11.91, which we see in the data from the spreadsheet. We can then set them equal and solve for mu, which we found to be 0.1973. Here we create the glow script code. First, we just create a magnet at the origin and calculate the magnitude of the magnetic moment using the mu we found before. We then define the dipole and visualize the magnetic field on the axis and perpendicular to the axis using various observation points. Finally, we visualize the magnetic field 45 degrees off axis using the average d-perp we found from the experiment. Our theoretical off-axis field is shown below, as well as the experimental off-axis field. The percent error is 14%, which is relatively low. So this is a good model to find the off-axis magnetic field. Some sources of error could include nearby magnetic fields that we did not account for in our calculations, an incorrect magnetometer location, as well as any kind of human interaction with the system, such as bumping it or moving it, could cause major differences in the data. Another thing is that a bar magnet is not a true dipole, but we assume it to be in order to simplify our calculations so we can solve this experiment. If we hadn't oriented our experiment to compensate for magnetic north, The X components would be different because magnetic north would contribute to the magnetic field measurements, and the Y components would also be different because we're not accounting for the Earth. If we were to do the experiment again, but rather with two identical magnets stuck together, end to end, our measurements would increase because of the combined magnetic field from the two magnets. We expect this because of the principle of superposition.